Okay, number one, find the domain of this function f of x, which is this big square root ln of x minus 1. Okay, so for these problems, you're looking for sort of all of the values that x can equal. And to do that, we're actually going to do it the opposite way. We're going to find the values that x can't equal. So for example, one we're going to use here is when you have a square root. You probably heard before you can't take the square root of a negative number. If you do like square root of -1, that equals I, and we're not doing that this early on in Purdue calculus. So for this case, like in this scenario, x would always be greater than or equal to 0. Can't be negative. So we're going to use properties like that to figure out what x can't equal, and then sort of reverse it, and then figure out what our domain of the function is. So for this problem, you always like start in and then work out. So we're going to start with the inside here, ln x minus 1, and then after that, figure out what the heck to do with the big square root here. We're just going to figure out the inside for now. So one of these properties that you'll use is whenever you have log of a number, ln is just log base e. So whenever you have a log, whatever's inside the log has to be greater than 0. So we're going to use that. So whatever's inside the log, x minus 1, it must be greater than 0. And then we just rearrange a couple things to get x back itself. So x is greater than 1. So that's our first restriction. I'll put it up in the corner here. X must be greater than 1. And then for our second one is we have to take into account the whole thing. And I just said before that when square root x must be greater than or equal to 0. So ln of x minus 1 must be greater than or equal to 0. And then we just simplify from here. So one trick that you'll have to do pretty often with these domain problems and in calculus in general is whenever you have a log all by itself on one side, one thing you can do is treat both of these sides as an exponent. And then the base you'll put on the left hand side here. So it becomes e to the ln of yada yada is greater than or equal to e to the 0. And then what this actually does is it cancels out that. So you're just left with this x minus 1 there. So it's x minus 1 is greater than or equal to e to the 0, which is just 1. Anything to the 0 is 1. And then algebra simplifies, so x is greater than or equal to 2. So there's our second restriction, and you'll actually see that this one that we just found already fully encompasses the one that we already found, this x is greater than 1. So we can actually just kind of forget about the top one and ignore it for now. I'll just cross it off instead of erasing it so you can kind of see what I mean. And yeah, so then we just, take this domain restriction here and sort of put it in the form that it wants over here. And it looks like it'll be C. That's our answer. What it's saying is that x starts at 2 and then ends at infinity. And that's exactly what we're saying here. X, it's greater than or equal to 2. So like if we have a number line and we have a point at 2, it then continues on. It's greater than, so it goes to the right, all the way towards infinity. And then everything to the left, like 1 and 0 and -1, it doesn't include that, so we don't have the line there. And that's exactly what C is saying. It starts at 2, ends in infinity. All the others are just sort of slightly incorrect versions of that. So like here is from 1 to infinity. No, it's 2 to infinity. This is only 1 to 2. Same with this one, does not end at infinity. And then this one, I don't know how they got this 1 plus e, so we know that's wrong too. So C is the correct answer. Oh, and then, so this didn't end up coming up in this problem, but you do have to pay attention to um, when it uses a bracket and when it uses a parenthesis. So, like in cases like B, there's a parenthesis here and a bracket here on the right. When you have a bracket, it means it includes that number. So it can be everything less than 2, and it can also equal 2. So like that's the case of x is less than or equal to 2. And then for the left-hand side here, the parenthesis, it means it's greater than 1, but it doesn't equal 1. That's what the parenthesis means. So it's just a greater than sign, not a greater than or equal to sign. So that's what that means. You'll probably have a couple questions like that on the exams you have. So just keep that in your pocket, keep that in the back of your mind. And yeah, that's how you find the domain of this one. Okay, question 2. The graph of a function f and its transformation g are pictured below. How is g related to f? So for these problems, it sort of gives you a function f of x, and then its final g of x transformation after you do a bunch of transformations onto it. So it's just asking what transformations do you need to do to f to get to g. And so like, do you have to move it left, right, up and down? Do you have to squish it down or stretch it up or squish it sideways, stretch it sideways? And you just have to figure out what order to put those in. So we can start by kind of ruling out some transformations that it didn't do. One that I kind of see right off the bat is um, if you kind of look at the oops, if you kind of look at the distance between like these humps here, like you see it kind of peaks there, peaks there. They're kind of the same for both of these, right? So here's the peak of G and the peak of F. The distance between them looks to be about the same each time. So based on that, we can kind of feel that it didn't like compress it or stretch it horizontally. So like if you had a function like this, it didn't do something where it like squishes it. So it didn't do like that. So we can kind of rule that out. Um, in the opposite direction, what we can kind of infer is that it's sort of squished horizontally. So like it kind of did one of these, because you can see um, in the original F, it like peaks there, peaks all the way up there. But in G, they're kind of closer to the origin. Like the distance between these, there's a big discrepancy when it comes to them and their kind of distance between them. So you can kind of tell that they are being squished. Now, what factor though? Like how much is it? How do you quantify that? Well, it will be a fraction. It will be something like that. And because we're doing it vertically instead of horizontally, you keep it outside of the f of x here. So it will end up being like out there. And knowing that, we can kind of uh, get it down to 2 answer choices. So not any of these. Um, and then so that's basically it for, compressing and stretching. But what about simply just moving it, like translating it left, right, up and down, however many units? And we can see back when we were figuring out if it was being compressed or stretched horizontally, we saw that it was being moved a little bit, right? So here's the peak of F. The peak of G is like a little bit to the left of it, right? Like it moved it that way. So it ended up being moved, looks like about 1 unit left. And whenever you're acting horizontally, you always make sure it's on the inside of the f of x. You always affect the x on it. So that would end up being f of, come on, f of x, and then we're moving left. So when you're acting on the inside, it ends up being plus. It's kind of backwards like that. Usually you'd think that when you do a plus, something positive, it always goes like to the right or up. But since we're on the inside of the function, you switch those operations around. So it ends up being a plus instead of a minus since we're going left. So it should end up being on the inside an f of x plus 1. And that's what this one looks like. So it looks like that one's our answer. All of the others are which is a little bit different, a little bit wrong. Let's look at the other one that was close, B. Uh, it did end up gauging that it was translated some number of units, but it did it in the wrong spot and ended up doing on the outside of the function instead of on the inside. Whenever you do it on the inside, it's horizontal. Whenever you do it on the outside, it's vertical. And there's not really any vertical movement, just vertical compression. So that one's wrong. And then for all the others, they ended up using a factor of 2 instead of a factor of 1/2. Whenever you have a large number, when you have a number greater than 1 there, it ends up stretching it horizontally instead of compressing it. And numbers like 1/2, yeah, it compresses it, which we saw. So E is the correct answer here. All right, number 3, find the inverse of this function ln of the quantity of e to the x minus 3. Okay, so this, to set it up is really easy. It's just the calculation that sometimes gets pretty difficult. All you do is imagine this as y equals ln of e to the x minus 3, and then all you do is swap the positions of the x and the y. So this becomes x equals ln of e to the y minus 3. And then you get it back to kind of its original position where you had y all by itself on one side. And you do that just, algebra, moving things around. So let's do that. So we'll use a trick that we did earlier in this exam where you, whenever you have a log all by itself, you just treat both of those as an exponent with base of that log. So it becomes e to the ln of all that, and then e to the x. And then that ends up canceling out the e to the ln, and you're just left with what's on the inside there. So that becomes e to the y minus 3 equals e to the x. And then we can add 3 to both sides. That becomes e to the y equals e to the x plus 3. And then we can take an ln of both sides. And then what ends up happening is this exponent gets put out there. So it becomes y times the ln of e. And then ln of e is just 1, so that gets canceled out, and then we're just left with y. So y equals ln of e to the x plus 3. And there we go. That's our answer. That's the inverse of this function. Okay, number 4. If the height of a ball is given by this function, this s of t, where t is given seconds, then the average velocity during the time interval from 0 seconds, right when it starts, to half a second is what? It's average. So let's get rid of those. So like this height function, it'll probably look something like this. Parabola, an upside down parabola, where you throw the ball up in the air, woo, and then kind of slows down, hits its peak, and then gravity, takes it all the way back down to the floor. That's probably what that one will look like. And then to find, its average velocity, well, that's a derivative. So that will probably end up looking like this, just a straight line going down, where, right at its peak, it's at its fast speed going up, and then, keeps slowing down, and then this point corresponds to that point when it hits its peak, and then as gravity takes it down, its velocity is now negative since it's going down. And then what it's asking is the average velocity during this time interval. Basically just take the velocity, so like find the velocity function, find this value, and find some value a half, and then average them. So basically just find this value. So basically what we're going to do here is just find the velocity function, which is just the derivative of s of t, and then plug in the average of these 2 points, which is a fourth. So let's go ahead and do all of that after I erase this. So s of t is negative 16t squared plus 10t plus 2. This is a fairly easy derivative compared to some of the stuff you'll be doing later on in the semester. You just move the exponent out there, and then reduce it by 1. So negative 16 times 2 is negative 32, and then t 2 minus 1 is 1, so that'd just be t to the 1, and you don't need to know that. That's just t. And then plus, so now we're looking at 10t, so t to the 1, take 1 out to the front, it's still just 10. And then 1 minus 0 is 0, t to the 0 is just 1, so that becomes 10. And then this constant 2, I mean, this is basically just a 2 times t to the 1. When you move out the 1, that doesn't, oh wait, hang on. I messed up, that's not t to the 1, that's t to the 0. When you move out 0 to the front, it becomes 0 times 2, which is just 0. And so you can kind of just ignore this constant here. So this is the derivative. This is s prime of t. Sometimes you also see it as v of t for velocity. Um, and then what we said earlier, you just plug in 1/4. Alternatively, you can plug in 0 and plug in a half and then, average them. But since it's just a straight line, then we don't need to do that. We can just directly plug in a fourth. So that's negative 32 times a fourth plus 10. 32 divided by 4 is negative 8. And 10 minus 8 is 2. So the average velocity during this time interval from 0 seconds to half a second is 2 feet per second. That's what it's saying. All right, number 5. Suppose f of x equals this big fraction. Then which of these are true? Which of these, so each of these has two limits. It's just, which two are true. And I don't really like this problem because it's really trying to trick you. It's just trying to mess you up based on like these here. This 2 minus and then this minus 2. It kind of wants you to, feel like they're the same thing, but really this one here is negative 2 and this one here is positive 2 coming from the left side. So the opposite of this one would be, so like these ones are to the minus, the opposite when you come from the right side would be, 2 positive. So that's just what they're trying to do here. They are kind of trying to trick you, which I don't like. So I'm gonna cheat a little bit. Instead of drawing this whole thing out, I'm going to show you what this looks like on Desmos. So this is what this function looks like. And let's sort of interpret what each of these are saying. So the limit as x approaches 2 from the left side. So let's look back at what our function looks like. As x approaches 2 right here from the left side. So as x keeps moving in this direction towards 2, where does it approach? And clearly it is going way up to infinity. As x approaches 2 to the left side, it goes up to infinity. As x approaches 2 from the right side, it goes towards negative infinity. It goes all the way down. And you can see the only ones with that answer choice are A and B, A and D. So now we just have the other limit to worry about as x approaches negative 2. So we'll look at that as x approaches negative 2 here. Well, I mean, don't really have to. Oh, right, there's a discontinuity there. Okay, so it's undefined at that point, but it's a removable discontinuity since it's still pretty continuous here. So, like, it's not, this big gap right here. It's still pretty much a straight line. It just has a hole. And that one ends up being, looks like a fourth, 0.25. I'll get to how to actually calculate these limits, but I just wanted to show you how they were kind of tricking you and what the answer will be, and then we'll sort of evaluate the limit from there. So we can tell it's so limit as x approaches negative 2 equals a fourth, so A is the correct answer here. Let's actually, can't pull out your laptop on a test, so let's show you how to actually do this. Okay, so you have this function here, and you define its limits. Um, What can you do? Oh, yeah, okay. So you just factor and sort of simplify this. So the on the bottom, this is a difference of squares, so you can factor that. So that's x plus 2 all over um, 2 plus x and 2 minus x. And then you can cross both of these out. They're the same. So that ends up being 1 over 2 minus x. And then, well, this one still won't work. Or, no, yeah, no, that's our answer. So as x approaches 2, that becomes 1 over 2 minus 2, which equals 1 over 0, which is infinity. So that's where they get this infinity from. And then as x approaches negative 2, we plug that in, so it's 1 over 2 minus negative 2, which is just 1 over 4. So that's how they get the 1 over 4 here. So that's how you would end up calculating this on a test. It's super crummy how they did both a 2 minus and a minus 2. Uh, they kind of, implying that they're the same thing, but they're not at all. So, uh, yeah, they'll do that to you sometimes, unfortunately. So that's how you'd end up finding the limits for this problem. All right, question 6. It gives you a graph, and it's asking you to find the graph of its derivative. So you just kind of have to understand what exactly a derivative is, which is just, the slope at any given point. So like as it's sort of rising up, its slope increases. So it starts off, pretty flat, and it keeps going up until the origin. So its derivative should also kind of, start at 0 and then go up, right? So, based on that, you can sort of cross off B because it's just flat all around. It clearly does not have a consistent slope because it's curving. Um, and then what next? So the other side is sort of doing the same thing, but in reverse. So that was pretty misleading if I drew that. It goes down. The slope decreases, or the slope is negative, but it still increases because it goes from negative to, less negative, less steep. So based off that, it looks like A would end up being, it looks pretty right because the left side is positive, it has a positive slope, and the right side is negative, so it has a negative slope, which is exactly what's going on here. It's rising and then falling. Um, and then okay, so what about this like break here in the right in the middle? So you can kind of see it sort of makes a point. It's not exactly a round sort of continuous thing like that. There's a definite like peak on this like hill there. And whenever you have that, that means there's going to be a jump in your um, derivative. So the slope is gonna, start at one point, it's gonna break and then pick up somewhere else. It just goes, straight down like that. And that's also exactly what A is doing. It rises up and then when it come on. And then when it hits that peak at the origin, then it immediately jumps back down and starts having a really negative slope. So yeah, it definitely looks like A is our right answer. All the others exhibit some property that we just said had to be there. Uh, C, D, and E all don't have that jump in the middle. They are all continuous there. So those are all out. And as we already said, B, it does have that jump. That's one thing it got right, but it's all flat. And that's not the case. When the derivative is flat, when it's just a straight flat line like that, um, that means that the original function, it has to be just a line, like a line going up or a line going down or a line going straight across. But can't be curvy, which this one clearly is. So can't be B, can't be any of the others. Looks like it's definitely A. Okay, number 7. Find a value for A that makes this function continuous for all values of x. And this is a piecewise function where it's defined differently for different values of x. So when x specifically equals 1, then it's just 3. So if we're going to start to graph this out, when x equals 1, then f of x that equals 3. This point right up here, 3. And then for any other point, left or right, any other value of x, it's going to be this big nasty function here. And what it's saying is it wants it to be continuous. So if you were to pick a value for a, and then let's say a is like 1, so that'd be x squared plus x plus 1 all over x minus 1. If you graph that out, it'll end up looking something like this, whatever shape it is. If you do a different value of it, or it might go under, or whatever. For it to be continuous, it has to end up hitting that point right here. And there should be one and only one value of a that makes the value of f of x here equal, sort of, hit this point here, make it equal to 3. And you do that, okay, so you'd usually do that via a limit. You'd find the limit as x approaches 1 for this, because we're trying to find it when it's equal to 1, and then sort of figure out the value of a from there. But I tried that already, and for the life of me, I could not figure out how to get it to work. So I'm going to do sort of a hacky workaround, and it's not the most fun way to do it, but it gets you most of the way. And if all else fails, they literally give you each of these values. So if you want to, you can just plug in a equals -2, a equals 0, and then find the limit as x approaches 1, and then figure out when it equals 3 for that. That's a last resort. I really do, like, this is the most complicated one of these questions that I've seen so far. So I doubt you'll get something like that on your exams, and it'll probably be simpler. But this is the way that I'm going to approach this problem. We're going to use our good old friend polynomial long division, except he's not a very good friend at all. I hate polynomial long division, but that's what we're going to do here. So we have a polynomial and another polynomial that we're dividing it by. So we're going to set that up. That's x minus 1 is the divisor, x squared plus x plus a. This is kind of a tricky process. I'm going to sort of speed through it, but you might want to look it up on your own. So x squared divided by x is x, and then x times x is x squared. X times -1 is -x, minus is 2x, and then bring down the a. So then 2x divided by x is 2, positive 2. 2 times x is 2x. 2 times -1 is -2. Subtract, that ends up being a plus 2. So that's our remainder. So what we just did here is we found a different way to express x squared plus x plus a. It's x minus 1 times x plus 2 plus a plus 2 all over the original, which is x minus 1. So remember, we're solving for what value of a would work. And this is the part where it gets kind of fuzzy. But it would be really nice, so since we're doing when x equals 1, this denominator would end up being 0 in this case. So it would be really nice if the numerator were also 0. If a plus 2 also equaled 0. That's a messed up plus sign. Because usually if you have, anything else in the numerator, that'd be like 1 over 0. That's infinity, and we don't really want that. So a plus 2 equals 0, so a is equal to -2. That is a terrible way to approach this problem. Maybe it'll work for you. If you get something simpler, it would definitely be easier. It'll probably involve greater than and less than signs, which are way better. I'm sure there's some other questions that I'll hit in the future regarding that, but for now, this is a way you can kind of do a problem like this if you have a function like this with polynomials and division. So that's how I approach this one. All right, number 8. Evaluate this limit, and it's this big fraction. So, uh, one one thing that comes in handy when you're doing limits is if you ever get something in a form you have a constant over a variable like x, like it's squared or some huge power or whatever, and then the limit is from x to infinity, that just becomes 1 over infinity basically, and that is just 0. So that sort of gets ignored in most situations. So that's what we're going to do here. We're going to try to get all of these x's in a form where it's 1 over them, and then we can basically just ignore them. So to do that, I think what we do first is um, in order to like modify both the top and the bottom easier, I think we'd have to expand this square root down so it affects both, like the whole fraction instead of just the top. And we can do that by just squaring the bottom and then also and then immediately taking the square root of it. So 4x to the 6 minus x all over, um, it'd be x cubed plus 8 squared, and then the square root of the whole thing. So you just immediately take the square root of the square, so it doesn't change the function. Okay, and then let's expand the denominator. So 4x6 minus 6 all over, let's see, x cubed squared is x to the 6 plus 8x cubed plus 8x cubed, which is 16x cubed plus 8 squared, which is 64. Okay, so now what we can do is divide both the top and the bottom by the same value, and that won't change the equation. Like if you have 6 over 3 and you divide both of these by 3, it ends up becoming 2 over 1, and this equals 2, and so does this. So divide both top and bottom by the same thing, and we'll have it'll still be equal to itself. So I'm thinking we do x to the 6th, and that's how we'll get back to this trick that we did earlier. So 4x to the 6th divided by x to the 6th is just 4 minus x over x to the 6th, which is 1 over x to the 5th. And then the bottom, x to the 6th divided by x to the 6th is 1. 16x cubed divided by x to the 6th is 16 over x cubed plus 64 over x to the 6th. X to the 6th. And cool, so now we have everything in this form that we had earlier where it's 1 over everything. So 1 over x to the 5th goes towards infinity. That just becomes 0. Same with this. That's also 0. That's also 0. Since we're just adding and subtracting all of them, they all become 0. You can ignore them. So then it just ends up becoming square root of 4 over 1, which is the square root of 4, which is 2. B. That's our answer. Okay, so number 9, how many vertical and horizontal asymptotes does this function have? So let's put this off to the side. Number of vertical asymptotes, number of horizontal asymptotes. Okay, so basically, so let's say function 1 over x, a simpler function. That looks like this. That's an asymptote. That's an asymptote. So it's one of each. We just have to do this for this larger one. So to find the horizontal asymptotes, you just set the denominator equal to 0 and solve for x. So x cubed plus x squared equals 0. Let's see if we can take out an x squared. So x squared times x plus 1 equals 0. And we can see that we have 2 asymptotes here, 2 vertical asymptotes. So 2. And then for the horizontal asymptotes, that's like this one. what you can do to just find the number of them, not even just, what the asymptotes are, just the number, is look at the degree of both the numerator and the denominator, the greatest degree. If you have n and d, if n is less than or equal to d, then there's always one, always just one. So in this case, there are one horizontal and two vertical, so D, that's our answer. All right, question 10. This gives you this limit, and it represents f prime of a, which is the derivative of a function f and at a certain point a, and it wants you to find the original function and a. So what it basically gave you here is just the filled in manual derivative at a certain point. Remember the manual derivative is f of x plus h minus f at x all over h. So basically it just filled all of those in. It filled in the f of x's and it filled in the x's. So it just wants you to figure out um, which of these functions, which of these a's would get it back in this state. So you can kind of, this is actually a pretty good problem to just brute force. Just plug in, um, just plug in A into F and then figure out if it equals this, 1 over E, because that would equal just F of X. So we can go ahead and do that. So A, that would be E to the 1 over E. Uh, that's E to the E minus, to the negative 1, which I don't think equals 1 over E at all, so that one's out. Uh, so B would be E to the negative 1 over E squared, which is E to the negative 1 over E squared, which is E to the negative E negative 2. That's looking pretty funky too. I don't think that's going to get back to just 1 over E, so that one's out. Uh, C, negative x squared equals 1, so that's just negative 1 squared, which equals 1. That doesn't equal 1 over e at all. D, x squared and 1 over e, so that's just 1 over e squared, which is 1 over e squared. Nope, that's a power too great. So looks like our answer is e. We can plug it in and see for ourselves. That's e to the negative 1 squared, which is e to the negative 1, which is 1 over e. So that's exactly this 1 over e is exactly equal to that 1 over e. That's from the original manual derivative function. So that's a quick way you kind of find one of these. If you wanted, you could actually take the derivative of all these and go, full force with it, but uh, find the limit. But I don't think you need to do it for a problem like this. So that's how you can quickly do one of these. All right, question 11, almost done. Giving this following data in this table, which equation is a tangent line to this function that we don't fully know? We just have a couple points that we know about it and a couple points of its derivative. So this would be useful to graph out actually. So do one of these. So what it's saying is when x equals 1, y equals 2, and at that point the slope is negative 2. So when x equals 1, y equals 2, it'd be right there, and its slope is negative 2, so it kind of goes down like that. And then same thing for the second one. So when x equals 2, f of x equals 3, which is up there. And then its slope is 2, so same steepness, just in the other direction. And it wants us to find, so which one of these equations is equal to one of these. So you could just brute force it and, plug in a 1, plug in a 2, and see if it equals one of those points. But that also doesn't take into account the derivative. So the easiest way to do this is just find the equation of these two lines. And to do that, well, we've got a point and we've got a slope, so we can just use the point slope formula, which is y minus y1, which is 2, equals the slope, -2, times x minus x1, which is 1. And then we simplify. So y minus 2 equals -2x plus 2, which equals y equals -2x plus 4. So that's our first equation. If we see, none of these exactly equal that. So it looks like whatever equation is the answer, it's going to correspond to this point. So let's go ahead and find that. So do the same thing, point slope formula, but for the second set of values, for this point and this slope. So y minus, not 2, that's y minus 3, which equals the slope 2 times x minus 2. Simplify, so y minus 3 equals 2x minus 4. Y equals 2x plus 3, so minus 1. And boom, D. Y equals 2x minus 1. That is this line. So boom, D. Okay, number 12, last one for this exam. Assume these facts about two functions h and k. These are just two, they're all real numbers. And then 3 definitions of sort of a piecewise function with multiple sort of definitions. And then it asks about what you can say about the limit as x approaches 2 of k. So you'll notice they're all asking about if the limit of k equals 7. Which is, this 7. That's what they're kind of asking about. And this would be really useful to graph out too. So let's go ahead and do that. So at when x equals 2, h of 2 equals 7. So that's h of 2 and equals 7. Okay, so for the limit of k to, exist, for it to exist at 7, then it needs to be continuous at that point too. So, whoops, that doesn't touch. Better accuracy is needed. So this would have to be k of x if we wanted that limit at 2 to exist. And fortunately for us, that's pretty easy to tie back to what these definitions already said, because these two basically just say that h and k are equal at any point other than 2. Like that, like there would be a hole there, but yeah, that's both h and k. And since we have a defined point for h, right there, as long as h is continuous at that point, then it means k will too. So that's B. So if h is continuous at 2, then the limit of k equals 7. And I'd really want to explain why C is not the right answer because it's really similar. I'll do it by giving a counterexample. So uh, let's say that k is continuous at x equals 2. That could just be that, you know? It's continuous, but the point there is not 7. It's, I don't know, 5 or whatever, or 4. So that couldn't be the case. It's only the case if h is continuous at that point, since we have it defined already at x equals 2. So that's why B would be the right answer here. Other ones not the case either. A is it says no other conditions are necessary, so prove that wasn't true. C, we said limit equals 7 if and only if both h and k are continuous. Well, that yeah, that's true. That would end up equaling 7 every time, but that's stating more information than we need. So we only need to know if h is continuous at that point, not if h and k are. So D's wrong. And then E says none of them are. Who knows? We don't have enough information, and any information we can generate probably won't be enough. So prove that wasn't right. So E's wrong too. It's B.